In this tutorial, I'll show you the easiest way to train AI agents to play Atari games. In fact, you won't even need to write a single line of code. It can be all done via command line interface. Although no coding is necessary, it is helpful to know Python, as the prerequisite is that you have Python installed and an environment manager like Anaconda or Miniconda. I will demo with Miniconda with Visual Studio Code on Windows, but this should work on Linux and Mac as well. A fact of life with software is that they change over time. That is why in this demo, I will use specific versions of the packages to install so that you can repeat exactly what I do in the video. I'm going to go to my Start menu and launch the Anaconda prompt. Conda create to create a virtual Python environment to hold the Atari games and the reinforcement learning library. --name, and I'll give it a name of Atari env. The version of Python that works with those libraries at the moment is 3.11. --yes to automatically answer any prompts. Hit enter. My virtual environment has been created. I'm going to activate it. You can see that the environment has been activated. We will install Gymnasium. Gymnasium is a collection of reinforcement learning environments. When I say reinforcement learning environment or environment going forward, I'm referring to the Atari games. So don't confuse that with a Python virtual environment. I'm going to scroll down here to get the command. I'm going to hardcode the version. I'm going to go to the Gymnasium GitHub page and click on Releases. And I'll find the latest stable release. It's going to be 0.29.1. This first package installs the library that can interface with the Atari games. The second package is the one that actually contains the games. And we'll use the same version. I'm not going to run the command just yet. In case you don't know, there is a difference between running pip install one package at a time versus all in a single line. When we do a single call, pip will attempt to resolve dependency conflicts for us, and that's what we want. Stable Baselines 3 is a collection of reinforcement learning algorithms. While we can use it for training by writing code, there is an easier way. RL Baselines3 Zoo, or I'll just call it RL Zoo for short, is a wrapper around Stable Baselines 3 that makes training possible using just command lines. We can go to Zoo's GitHub page, scroll down to the release section to see what version that we want. When we install RL Zoo, it will install Stable Baselines 3 for us. Let me get the command. Version 230. There are two more dependencies that we need. Let me paste that in here. OpenCV is used for image processing since we will train using computer vision. In other words, the AI agent sees the game as a sequence of images or frames. After training, we can use MoviePy to record the AI playing the game. Okay, let's run the install. Okay, that looks good. We have one more install, but this only applies if you have an NVIDIA video card and you want to use it to speed up training. We need PyTorch, an open source framework for deep learning. When we install RL Zoo, PyTorch was automatically installed as a dependency. However, GPU support was not enabled. We need to uninstall PyTorch and reinstall it with GPU support enabled. We see Torch here. Note the version that we're going to reinstall, 241. I'm going to uninstall this. Now I'll go to PyTorch's website, scroll down a little bit, select these options based on your system, copy the command, I'm going to remove Torch Audio and Torch Vision since we don't need to use those, and I'll hardcode the version that we had before. == Note that pip and pip3 are the same, so we'll just run this as is. Okay, install is done. Let me list it again. We see PyTorch here. The CU118 indicates that we have the CUDA library version 11.8 installed. CUDA is another word for GPU compute. Now that our Python virtual environment has all the libraries that we need, I'm going to switch over to Visual Studio Code. First, I'm going to make a new empty folder as my project. I will call it Atari. I'm just going to right-click on an empty area and select Open in Code. In Visual Studio Code, I have my empty folder open. I'm going to hold Ctrl-Shift-P and select my Python interpreter. If you don't see this option, then start typing Python, and then you should see it on the drop-down list. I'm going to select the environment that we just created over at the command prompt, and it's called Atari env. Now I'm going to open a new terminal. You can see that the terminal automatically launches within our Python virtual environment. We can start building out the command line that we're going to use for training. We'll train something easy, such as Breakout. We'll start with Breakout because we can see improvements within minutes. More complex games could take hours or days before seeing much results. In my command line, I'm going to say Python -m to run a module, and the module that we're going to run is RL-Zoo3.train. We will be passing in quite a few options, and I'll be walking you through each one. --algo to pass in the reinforcement learning algorithm. How do you know which algorithm to use? I'm back at the RL Zoo GitHub page. I'm going to open the hyperparameters folder. Within this folder are all the algorithms available in Stable Baselines 3. However, we do have a limited selection for Atari games. Let's take PPO for example. Up at the top, you see that there is a Atari configuration here. This indicates that we can use PPO for training Atari games. If I click on SAC, it does not have Atari anywhere in the file, so we will not be able to use this one. Going back to PPO, these hyperparameters affect how the learning algorithm functions. We won't be talking much about the parameters in this video. If you don't know much about reinforcement learning algorithms, start with PPO, and that's what we're going to use. --env to specify which game we want to train. Going back to my Gymnasium Breakout page, this is the environment ID. We need to use --env-keyword arguments to pass in a little bit of configuration for the Breakout environment. If I scroll down on the Breakout page, you can see that there are a bunch of variations of this game. The one we selected is the Breakout version 5, which is the latest one. These are all the same games, but these three columns tells us what the differences are between the variations. Without going into too much details on this table, we select the latest version. We are training based on vision, so we're using the RGB or red, green, blue pixels of the frames. So we are not training based on RAM or what's in the game's random access memory. Frame skip lets our agent process every fourth frame rather than every single frame. This technique speeds up training. The Stable Baselines 3 Atari wrapper already takes care of frame skipping, so we need to reset this to 1. Repeat action probability adds a bit of randomness to the game with the intent to make training harder. We don't really want to make training harder, so we're going to take out this 0.25 and reset it to 0. I'll take the keyword frame skip, use a colon to pass in the value. We want to reset it to 1. Take the keyword repeat action probability, space, and pass in our second configuration. We want to reset this to 0. Next, I'll go back to the hyperparameters. This parameter here, n_environments, means that we're creating 8 copies of the game and training them all in parallel. If you have a more powerful system, or maybe one that's not so powerful, I'll show you how to override this number. Down here, n time steps is how many steps you want to train the environment. Each step is one action performed by the AI agent, and it's set to 10 million by default. 10 million may not be enough. I'll show you how to override this and pass in a much larger number. We'll use -- hyperparams, use the keywords that we just saw. Instead of 8 environments, I think my laptop can handle 12, and then instead of 10 million steps, I'm going to do 100 million. Now that we have our training environment set up, we need to create an evaluation environment to test the model during training. If a test result beats the prior test result, then a new best training model is saved. I'll paste the whole thing and then I'll explain each one. This says I want to create one environment to do evaluation. I want to evaluate it for one episode, meaning the AI plays until it dies. I'm going to do evaluation every 100,000 time steps, and I'll pass it the same frame skip and repeat action probability as before. In addition to saving the best model, we can save a trained model every X number of steps. This is called creating checkpoints. This is useful if we want to compare how the model performs after training for, say, 1 million steps versus 2 million steps, and so on. Since it takes many millions of steps to train a model, I'll set this value to 1 million steps. -- save frequency 1 million. In order to enable parallel processing, I need to do -- vector environment equal to subproc. Now let me show you how I know to use these parameters. Of course, the RL Zoo documentation gives some examples on how to construct the commands, but it's not complete. Back to the RL Zoo GitHub page, go into RL Zoo 3, go into train.py. This is the module that we're calling right now. You can see all the arguments listed here. The one we just added, the vector environment one, you can see the choices are either dummy, which is to not use parallel processing, or subproc, which enables parallel processing. All right, we're almost done here. The next one is log interval. This affects how often logs are printed out on the screen. I'll set it to 10. I'll show you how that 10 affects the logging in a second. Now the last option I want to enable is progress. This is going to give me a progress bar down at the bottom to show me the training progress. Okay, finally, we can start training. Let's execute this command and get things going. You can see that it's taking the hyperparameters from the PPO YAML file. We overrode the number of environments to 12, and we overrode the time steps to 100 million. You can see that it created 12 environments plus one evaluation environment. Now you should see 12 of these plus one test environment. Here, using CUDA device indicates that it is using my GPU, and it's logging the training results into this path, which it created right here. The pattern is logs, the algorithm, the environment, plus a unique integer at the end here. Earlier, I passed in 10 as the log interval, so every 10 iterations, it will print out this table here. And an iteration is an update to the training model, so after 10 updates, we do this printout. Now, if I open my task manager, you can see my GPU being used here and how much CPU is being used. You want to balance the CPU, memory, and GPU usage. If you see that CPU, memory, or GPU is being maxed out, then that means you need to bump down the number of parallel environments. Sometimes Windows doesn't report the GPU usage very accurately. What we can do is open a new terminal. I'm clicking on this plus sign here. In the second command prompt, I can call NVIDIA SMI. Using this command, you can see the real GPU usage at the moment. Call it again if you want to see an update. Now back to the first terminal. We can see that there is a new best model already created. Since we just started training, this best model isn't going to be great, but let's run it anyway and see how it performs. Go back to my second terminal. I'm calling the enjoy module, passing in the same PPO algorithm, the same breakout environment, give it the folder of the training, logs. It's able to use the algorithm name and environment name to know that we're referring to this one. Also, we need to pass in the experiment ID, the ID of 1, which is this one here. If we start another training using the same options, we're going to see a_2 here for the next set of folders. So pass in -- load best. This should load the best model and run the game. Let's see. Hey, if you're finding value from this video, be sure to subscribe and thumbs up. And make sure you leave me a comment if you are able to train one of these games. Now going back to the training terminal, let me explain how to read this table so you can understand the training progress. Episode length mean, this is the average number of steps the agent takes per episode or before it dies. We should expect an upward trend, and it does have an upward trend. We can see this table versus this table, it is improving. The AI agent is able to survive for longer. Episode reward mean, this is the average number of rewards obtained per episode. The AI agent is rewarded by staying alive and by breaking blocks. So we should expect that over time, the amount of reward it collects will also improve, and it is slowly improving. Now for the next set of numbers, let me go all the way down so we can see the training progress. FPS is the frames per second. This is the speed at which the agent is interacting with the environment. This is the average. Down here, iterations per second is the same as frames per second. Obviously, the higher the number, the faster we're training. You can use this as an indicator to see if increasing the number of parallel environments actually increases the training speed. Iterations, as we talked about before, is the number of updates to the AI model, is how long we've been training. Total time steps is how many steps we've been training. If I scroll back all the way down, this is easier to look at. We've been training for 7 minutes, and we've been training for almost 500,000 steps. Remember earlier, we wanted to train for 100 million steps. This number, 27 hours, is how long it would take for us to train for 100 million steps. But we don't actually have to wait for it to finish. If you feel that the best model is already good enough, you can stop the training. Also, it's possible to stop the training anytime and resume it at a later point. And let me show you how to do that. I'm going to hit Ctrl+C to cancel the run. So I just terminated the training. You can see that it saved the model at the point of me stopping the training, and it's saved as ALE breakout v5.zip. Now to resume the training, let me bring back my original command. This was the command to start training. To resume training, I need to pass in -- trained - agent. I want to pass it the model that was saved when I cancel the run. So right click on here and choose copy relative path. Paste, enter. You can see that it created a second experiment. We can collapse this one and expand this one. We can see down here, it loaded a pre-trained agent and it started a new experiment folder. Even though it continued from the previous training, the number of steps is reset to 0. So it's going to go from 0 to 100 million again. But as long as it continued from the prior model, this is fine. We can cancel whenever we want. Okay, so we've been training for quite a while. 38 million steps. All right, let's see how our model performs. This time I'm going to record a video. I'm calling the record video module, and I want to record the agent playing for 5,000 steps. You've seen these before. We want to record the AI playing for 5,000 steps, pass in the log folder, load the best model. Also, we need to pass in the experiment ID, experiment number 2, hit enter. A new video folder popped up right here. Alright, recording is done. Let me open the video in a actual video player. The score is the 3 digits on the top, and the AI player has 5 lives, and it just lost 1. The number at the top right, the 1, I'm not sure what it is. A quick intro to deep reinforcement learning while the AI is playing. The paddle starts out moving around randomly. As it receives feedback from the game, it learns the value of those actions that it had performed. Breakout is considered easy because the paddle has a fairly high chance of randomly hitting the ball, and it is almost constantly receiving feedback from destroying the bricks. And our AI agent just lost its last life. Looks like it's going to need a little bit more training. Contrast that with a game like Pitfall, where there are multiple screens and a variety of obstacles. Imagine how hard it is for the character to randomly approach the alligator lake and randomly jumps to grab the vine. The chance is extremely low. In other words, some games may take weeks to train or not at all. So I just want to set your expectations before you jump in, and I'll leave you with that. Thanks for watching.